So hello, myself Neha. We have been asked by the IS activity to design a composite wall for cloud storage. First of all, composite wall means the iron wall which is been ironed by various types of layers. So let's see. We have been given some data for the question like the internal temperature is minus 20 degrees Celsius, external temperature is 35 degrees Celsius. We have to consider our wall number as AB. So considering 17 as AB. Here are some other parameters that we have to consider and we have to given. So the total wall thickness is 0.20 meters. The concrete layer is 5 centimeter. The insulation between them is 10 centimeter, and the FRP that is 5 centimeter. And the temperature difference in delta T is 55 degrees Celsius. So first of all, we have to find the area where we can where we have to assume AB mod 3. So for example, my roll number is 17. So assuming mod of 3 is 2 and 2 is 1. So putting the above value in heat transfer coefficient, like we have to find the heat inside and heat outside. So it will be 25 plus 2, that is 27 watt per meter square Kelvin. So here you can see I have considered this. The problem gives us the formula that is area is equal to 5 plus 0.05 to AB. So AB is 17. So the area we calculate is 5.85 meters square. So for finding thickness of each layer, we have to consider this inner and outer heat coefficient. So first of all, thickness layer outside concrete is 5 centimeter and inner FRP is 5 centimeter. Middle insulation is 10 centimeter in total. So first insulation thickness that will be 6 minus AB into mod 3. That becomes 6 minus 2 is equal to 4. So among these parameters we have to consider any 2 to 3 layers. So here I consider VIP layer that is 4 centimeter in thickness and that has a resistance of 0.004. Middle root that is 3 centimeter thickness. So the total thickness becomes 20 centimeter considering the concrete and other blocks. So here is the schematic diagram. So as you can see, the first layer is concrete that is 5 centimeter. Second one is VIP and is 4 centimeter. And another PUF and middle root is 3 centimeter respectively, and the FRP is 5. So the total diagram becomes 20 centimeter. So these are the parameters we come to know till now. AB is 17, heat inside is 27 watt per meter square, heat outside is 13 watt per meter square, and wall area is 5.85 meter square. So this is the selected insulation layers. So this is the order how our wall is going to be fit. These are some formulas that we are going to use for our next parameters. First of all, convection rate. So convection R is 1 upon H, conduction is L upon A, and the total resistance of all these we have to make the sum of all the resistances. Heat flux Q, we know that it is delta upon R. So here is the calculation for each and every layer. For convection, R naught is equal to 1 upon H naught is equal to 1 upon 13. That becomes R naught is equal to 0.0769, and similar for R I, that is 1 upon HI, that becomes 0.370. Conduction, that we know that R is equal to L upon K. So analyzing that for each, first of all concrete, it becomes 0.0278, and so on for VIP, member and FRP. We have to calculate the resistances. So now we have to make the sum of all these resistances. So here the total resistance becomes the sum of all internal resistance, outside resistance, and all layer resistance. That becomes 12.425 meters square Kelvin per watt. So now we have to calculate the heat gain. So we know the heat gain is delta T upon R. So we have the delta in our given unit, that is 55, and R that we have found is 12.425. So we have to divide 55 by 12.425. So heat gain becomes 4.23 watt per meter square. And the total refrigeration load, we have heat gain into area. First of all, we calculate the area of the layer. So the equation becomes 4.43 into 5.85, that is heat gain into area. So the total refrigeration load becomes 25.9 watt. So let us analyze the layers through resistance contributions. So as we come to know that outside convection has a resistance 0.076 and has contributed 0.6%. Considering all the layers, we come to know that the VIP layer that has 10% concentration, that has 10% resistance and 80.5% of contribution in the total layer of the wall. So controlling resistance, we come to know that VIP layer has more contribution, that is around 80%. So most temperature drop occurs across VIP. It controls heat flow as well as this is the main reason why refrigeration load is very low. So diagonal analysis means we have this I spoke now VIP is contributing around 80%. For insulation resistance now, VIP will be now 8.696 as we will divide the resistance by Rn divided by 1.5 and the puff will become 1.043 as well as the will be 0.652. So making it at a total, making the addition, it becomes 10.866. Heat flux, this is the second total. Means first of all we have calculated the layer 1 total and this time we will calculate the second. So heat flux for the second one is QH, that is 55 divided by 10.866 as total it is 10.866. So dividing it, it will heat flux will become 5.06 watt per meter square. And for the load second, the same formula applies. Q is equal to 0.56 into 5.85 is equal to 29.61. So here, as we can see, the load has increased by 40%, means around 40%. As we come to know before, so our first load is 25.9 watt, and the second come to that is 29. So it has increased up to 14%. So sensitivity, checking the sensitivity. If insulation K increases by 50%, new load will be 29.6 watt. Increases by increasing 40%. Design will still be robust, means will be in good state. Analysis of the cost. VIP cost share is 6,000 per meter square. For per meter total line, total work cost will be rupees 4,388 rupees. Approximate, not it is up to 4,380 rupees. So coming to the conclusion, we have optimized the composite wall in a low refrigeration load. Also, it is called cost-effective hybrid insulation. It is moderate in cost, not too much high, not too much low, and has a high thermal resistance. Thank you.